जी स्क्रीन शेयर होगी क्लास?
जी सर।
चलें देखिए आप।
This is an introduction to spectrophotometry, where I hope that we will learn
ये
some of the
आपने पढ़ा ही होगा,
fundamentals
लेकिन इसको
of
दोबारा रिव्यू
Beer's
करते
law.
हैं हम।
Let's start off by taking a look at a couple samples. Here I have a pair of food colorings, one red, one green. Both are in cuvettes. These are standard food colorings that you can find from.
ये क्यूवेट होती हैं, इनके अंदर आप सैंपल डालते हैं। अच्छा, इनकी एक साइड जो होती है ना, वो ट्रांसपेरेंट नहीं होती, और एक साइड जो इनकी दो साइडें इसकी जो है ना वो ट्रांसपेरेंट नहीं होती और दो ट्रांसपेरेंट होती हैं। जब आपने इसको स्पेक्ट्रोफोटोमीटर के अंदर रखना है तो जो ट्रांसपेरेंट होगी वो आपने लैंप वाली साइड पे रखनी होती है, और उस साइड से आप इसको कभी भी नहीं पकड़ते। और ये डबल बीम के अंदर एक के अंदर सैंपल डाला जाता है और दूसरे के अंदर उसका रेफरेंस है। रेफरेंस वो होता है जिसके अंदर आपने सोल्यूशन बनाया होता है।
From the grocery store, and I've got a red laser pointer, and what I'm interested in is looking at what happens to the laser pointer as we shine the light through the sample. Start off with the red one. As we move the sample into the beam of light, we see that the light doesn't appear to have any change. It's just as bright with or without the sample in the length of or in the path. Compare that to the green. We notice that there is a change, a noticeable change in the intensity of the light as the red light goes through the green sample. Not all the light is being transmitted, or put another way, it looks as if some of the light is being absorbed. We can also look at how concentration affects the amount of light that is transmitted. Here we have two different
अच्छा,
samples.
इसमें एक बात और कि आपने ना सैंपल अपना डाइल्यूट लेना है, जितना डाइल्यूट होगा उतना रिजल्ट आपका अच्छा आता है।
They are the same dye, just two different concentrations. And we'll start off with the dark one as we had in the previous section, shining light through it, and we see that some of the light is absorbed. Now if we use the lower concentration, we see that while some of the light is absorbed, it is not as much as the darker sample. So more light is being transmitted with the lower concentration. That suggests that there is a relationship between the amount of light transmitted and the concentration of the dye. In the last part of this demonstration, I want to take advantage of these cuvettes, which have a nice little feature. One side is thick. There's that's around 1 centimeter thick, and then we can rotate on its side and see that it's only about 3 millimeters thick. What this allows us to do is shine the light through either a large amount of the sample or a small amount of the sample. So let's start off again with going through the 3 millimeter length of solution. This is the same thing that we've been doing all along, and we see a absorption of the light. Now when we move to the 1 millimeter, we see that a lot more of the light is absorbed. From this we can conclude that the path length also has an effect on the amount of light that's going to be absorbed from a sample in spectrophotometry. Let's go ahead and summarize some of the observations that we've made. We saw that the red dye solution transmitted most, if not all, of the red laser light. However, the green dye solution absorbed some of that light. Saying that it absorbed the light is just like saying it did not transmit all of the light. When we had a dilute green solution, that one absorbed less light than the concentrated one. And we also observed that the longer path length resulted in more light absorption. We can analyze these observations by saying that the transmittance and the absorbance of light depends on the components in solution. We might also be able to hypothesize that the wavelength of the source light is important. However, since I didn't have a green laser light to test this hypothesis, we can't say too much about that in this video. We also observed that absorbance was decreasing with decreasing concentration, and we can make a claim that absorbance increases with increasing path length. Let's go ahead and try to depict this experiment diagram or schematically. We have a source, a sample, and a detector. The detector in our case was just a piece of white paper and our eye. The source was our LED laser, and the sample is the cuvette. What we're trying to do is measure the amount of light that's coming out, so the intensity of the light coming out of the sample relative to the intensity of light that's going in. I out divided by I in. We're going to call this ratio transmittance, and we're also going to define the absorbance as the negative log of this value. So there's a relationship between transmittance and absorbance. We're going to focus on absorbance because it turns out to be the more useful term. When we added a sample, the red sample did not appear to absorb any of the red laser light. We can say from that the sample transmits light of its own color. And when we moved to the green sample, we saw that the green sample absorbed quite a bit of light, and less light was transmitted. Change in the concentration of the sample changed the amount of light that was transmitted, and we were able to change the amount of light that was transmitted by changing the sample path length. Smaller path length led to more light being transmitted or less light being absorbed. All of these phenomena are brought together in what's called the Beers-Lambert law. So if we were to measure the same solution at various dilutions and plot the absorbance that we measured versus concentration, we would get a straight line. That straight line corresponds to this equation, A equals epsilon BC, where A is the absorbance, epsilon is the molar absorptivity, B is the path length, and C is the concentration. The Beers-Lambert plot is a special type of calibration curve. A calibration curve allows us to look at the relationship between absorbance and concentration, and is a typical method for analytical chemists to determine the concentration of unknown solutions. We plot a series of experimental data as a function of the concentration, and then use a best fit line to extract a meaningful equation from that data. We can use the best fit of the Beers-Lambert law to figure out the concentration of an unknown. Say, for example, an unknown gave a result or an absorbance of 0.12. We could find that on the y-axis and find where the best fit line crosses that point, and we would see in this particular hypothetical case that it corresponds to a concentration of about 0.4 molar. So as long as we know the best fit line and we've kept all of our parameters constant, we can use Beers-Lambert law to determine the concentration of the unknown. And that's what is frequently done in a variety of experiments using spectrophotometry. Now let's focus on the slope of this line just a little bit more. We notice that if the path length is constant, then the slope of this line is equal to the molar absorptivity. If the slope is large, then that indicates that the molar absorptivity is also large. A large molar absorptivity indicates that a sample has high sensitivity to light at that wavelength. In our example, we saw that green was very sensitive to the red laser light, and so we would predict that it would have a high slope and a high molar absorptivity. Compare this to the red dye, which showed little sensitivity to the red light, and therefore it has a very low slope or low molar absorptivity. The molar absorptivity of a dye is dependent on the various wavelengths, and we can see in this figure called a visible spectrum that different food colorings have different intensities at the various wavelengths. The peak intensity is called the lambda max, which is a quantity that helps us identify various dyes or substances that absorb in the visible spectrum. To conclude, after watching this video, there are several objectives, learning objectives that you should have met. You should be able to define the relationship between concentration and absorbance and name that law. You should be able to explain the basic principles of spectrophotometry both verbally and through sketching a diagram like we did earlier on in this video. You should be able to apply Beer's law to determine the concentration of an unknown. You should also be able to distinguish between absorbance and transmittance, knowing what the definitions are of the two and being able to convert mathematically between transmittance and absorbance. You should be able to design a calibration curve, and you should be able to evaluate Beer's law to determine the molar absorptivity.
जी क्लियर है। ये था बेसिक प्रिंसिपल जो है ना आपका स्पेक्ट्रोफोटोमेट्री का। अब हम नेक्स्ट स्टार्ट करते हैं आपका जो प्रैक्टिकल है।
Hi, my name is Amanda, and today I'll be talking to you about the experiment Spectrophotometric Determination of Iron. In this experiment, you'll be applying the Beer-Lambert law to quantify the amount of iron contained in an unknown sample. In this experiment, you're going to be preparing various solutions. There are sort of two groups of solutions. One will be a standard iron solution that you'll prepare in a 500 milliliter volumetric flask. This contains a known amount.
अच्छा, यहाँ पे जो ये जो स्टैंडर्ड कह रही है ना, ये हमें पता होता है कि इसके अंदर ये इतनी कंसंट्रेशन है, यानी कि ये स्टैंडर्ड आपका नॉन कंसंट्रेशन का होगा। क्लियर?
Amount of iron. The other flask that you will prepare is the unknown sample, and that will be done in a 250 milliliter volumetric flask. When you've prepared these solutions, they'll be transferred out into a series of 50 milliliter volumetric flasks shown here. The standards will contain different amounts of the standard iron added to the flasks. The unknown will be a certain amount of iron from your unknown sample, and that will be transferred in 250 milliliter volumetric flasks. To the standard solutions as well as the unknowns, you're going to be adding a couple of reagents before preparing them to the markings on the volumetric flasks. The first ingredient that you're going to add is hydroxylamine hydrochloride, and this is a reducing agent that takes the iron from your standard solution in the 3+ oxidation state down to the 2+ oxidation state. The second reagent that you'll add is orthophenanthroline, which will react with the iron 2+ and form a colored complex, and the color being orange, as you can see here. You'll let those ingredients react for about 10 minutes, and then you will dilute them to the mark with distilled water. So to kind of show you an example here, what you can do to sort of speed up your preparation is fill up the flask with distilled water around to where the neck starts, and then you'll add distilled water a little bit more slowly with your wash bottle and fill it up to where the line is on your flask. When you're preparing any solution with a volumetric flask, you want to ensure that you invert several times just to ensure that your solution is thoroughly mixed. Once you have prepared your standard solutions and your two unknowns, you'll then be ready to run your measurements on the spectrophotometer. The spectrophotometer that you'll be using looks like this. It's got a USB cable that connects it up to a laptop computer containing software that you're going to be using to run your measurements. The lamp of the spectrophotometer is on this side, and the detector is on this side. It has a holder that will be able to contain a cell where you'll put your sample in. The cell, or otherwise known as a cuvette, looks like this. It's got a clear side and it also has a graded side. And you want to ensure that the clear side is facing the detector and the lamp. So it will go in kind of like that. You don't want the graded sides facing the detector and the lamp, since that's going to redirect the light that's going through the sample. When you're running measurements with the cuvette as well, you always want to ensure that the clear sides are clean. So you can always do that by taking a Kleenex and holding it by the sides of your cuvette and then just giving it a quick wipe. Like that. So we're going to run some measurements. So at the start of the lab, you'll want to start up the Logger Pro software that's located on the desktop computer. Okay. And we have to first calibrate the instrument. So to do that, we're going to go into Experiment and go down to Calibrate and click on Spectrometer. And you'll see a window pop up telling you that the lamp is warming up. When the warm-up has completed, it'll then prompt you to place your cuvette in your device. So you would start off with your blank solution, so the one solution in your standard series that contains 0 milligrams of iron. And then you will put it in the spectrophotometer and then click on Finish Calibration. And after a few seconds, you'll then be able to click OK, and your spectrometer will be ready to run your experiment. You're going to be taking the 0.15 milligrams of your standard solution, and you're going to run this in your cuvette and place it in your spectrophotometer. So then to run your absorption spectra of your solution, in the Logger Pro window, you're going to click Collect. And it'll take a few seconds, but then you should be able to see a graph representing your absorption spectra of iron. You can then click Stop to collect the graph. And then if you want to make it a little bit clearer, you can do various things like take out the rainbow part of the spectrum just by sort of right-clicking the graph and go into Graph Options and uncheck Draw Visible Spectrum. So you'll want to save this spectra in a Word document for your lab report, and to do that on your keyboard, you can hit Function Print Screen. And open it up, and open up a Word document. and paste the object in Word and save the file so that you can print it off later on. So once you collect the spectra, you then are going to set up the graph for your series of standards to create your calibration curve. We're going to need to set up the graph so that we can record the absorbance and concentration of our solutions. To do that, we're going to go into Configure Spectrometer. And under collection mode, we're going to check off absorbance versus concentration and change the units to milligrams of iron per 50 milliliters, since that is how you prepared your solutions. And then you're going to select individual wavelengths under the drop-down menu and click Clear Selection just to remove any other items that might have been previously checked off. And you're going to select the maximum wavelength that you generated from your absorption spectrum. So ideally, for this experiment, you're expecting a maximum wavelength around 510 nanometers. So you'll check that off and then click OK. If you get a message popping up asking what to do with your latest run, so your absorption spectra, since you've saved it in Word and ensure that you've saved it in Word, click No. So now the graph has been set up to collect absorbance and
अच्छा इसमें ये देख लें
concentration
कि यहाँ पे
values.
आपकी जो मैक्सिमम जो है
You'll
ना वो
also
आ गई है.
see
इसके अलावा
some
ये
displays
भी
on
इसके अलावा ना बेटा ये भी हो सकता है कि जैसे यहाँ पे आपकी पीक आई थी ना, तो आप इसके ऊपर कर्सर रखें तो कर्सर जो है ना वो आपको बताता जाता है कि ये यहाँ पे ये है ये है ये है, तो उसमें भी रख के ना आप जहाँ पे मैक्सिमम होती है तो उसको क्लिक करके तो वो भी वैल्यू ले सकते हैं. ये वैल्यू हमें चाहिए होती है कि एंड पे हमने ना सबका जितने भी आपके पास वो स्पेक्ट्रा आएंगे या जितने सैंपल आपने रन किए हैं तो उनकी मैक्सिमम ये वैल्यू लेके तो आपने एक ग्राफ ड्रा करना है, वो जो लास्ट वीडियो के अंदर वो बेल लैम्बर्ट के लिए था, इसलिए ये वैल्यू ये नोट की गई है अब्जॉर्बेंस.
the left-hand side, sort of showing the real-time measurement of your sample. So now for the next part of the experiment, we're going to run our series of standards and construct our calibration curve. So to do this, we're going to start off with our lowest concentration of our standard solution, and we're going to work up to the highest concentration. So anytime you change samples, you're going to want to rinse the cuvette out once or twice with the solution that you're going to use to measure it. So just like so. Just to remove anything that might have been left over from the previous measurement. And then you'll fill it roughly 3/4 of the way. And just give the cuvette a quick wipe. And we're going to place it in our spectrometer. And then when you're ready to take your measurement, you'll then click Collect. And what you should see on the displays on the left side, you'll see the absorbance actively being displayed and a data point showing up on your graph. When the absorbance reading is more or less stable, you'll then click Keep, and a window will pop up prompting you to enter your concentration value. So this one is our 0.05 milligram of iron sample. We'll click OK, and then the point will show up on the graph and also be recorded in the table. You'll then rinse out the cuvette and put in your next solution, and then you'll click Collect again and then click Keep, and you'll keep repeating this for all of your standard solutions. And once you finish collecting your data points, you'll then click Stop. So when you finish running your calibration series, you'll get a graph that looks something like this. We're then going to have the program.
अच्छा, इसमें इसने पता क्या किया? आवाज आ रही क्लास आपको?
यस सर।
अच्छा, इसने इसी के ऊपर जो है ना वो एक कि वो ऑब्जर्वर्स लेके तो वो यहाँ पे मेंशन करती गई है। आप ये भी कर सकते हैं कि हर एक स्टैंडर्ड की वैल्यू लेके ना, जैसे लास्ट पे उसने यहाँ पे वैल्यू लिखी थी कि ये है, ये है, ये है, इतनी सारी हर एक कंसंट्रेशन के अगेंस्ट आपके ऑब्जर्वेंस आ जाएगी। तो ये आपके ऑब्जर्वेंस है ना, तो इधर कंसंट्रेशन है। तो ये पॉइंट आप खुद जो है ना वो मैन्युअली भी कर सकते हैं। करके उसके बाद आपके पास जो अननोन होगा ना उसके ऑब्जर्वेंस नोट कर लेनी है। ऑब्जॉर्बेंस से आप क्या करेंगे कि सपोज इतनी ऑब्जॉर्बेंस है तो ये आपके पास लाइन आ जाती है, इधर से लाइन ड्रा करके उसको डाउन करेंगे तो यहाँ से आपके पास कंसंट्रेशन आ जाएगी कि ये जो अननोन था उसकी ये कंसंट्रेशन है।
Place a linear fit on our points, and to do that, you're going to click on the button up here called Linear Fit. The graph will then display a line going through your data points and also give you information about your calibration curve, things like the slope and the y-intercept and so on. Make sure that you print screen this graph as well and paste it into your Word file. Once you have run your calibration series, you'll then measure your unknown solution. So we'll take some of our unknown. Again, make sure you rinse out the cuvette with some of the solution. Give it a quick wipe. Place it in the spectrometer. So once you've put in your unknown solution in your spectrometer, the absorbance will be measured automatically in the live display. You'll record this value in your lab notebook and then take out the sample and repeat the measurement for your second unknown flask. Once you obtain these values, you'll be able to use the calibration curve as well as your unknown absorbance values and determine the concentration of iron in your unknown solution.
जी, क्लियर हो गया क्लास? चाहिए जो इसके पास ये जो है ना ये फ्यूमिगेट है, ये इनके फ्यूमिगेट देख लें और हमारे पास जो पाकिस्तान के अंदर है वो देख लें। चले एनी आओ, ये क्लियर है आपको?
जी सर। सर ये हमारे लैब में हो जाएगा ना ये वाला एक्सपेरिमेंट?
बिल्कुल हो जाएगा, क्योंकि अभी हमारे पास जो है ना वो डबल बीम स्पेक्ट्रोफोटोमीटर है। बिल्कुल हो जाएगा। वो 119 लैब के अंदर नहीं, जो दूसरी केमिकल के साथ वाला छोटा रूम, वहाँ पे वो डबल बीम पड़ा हुआ हमारे पास स्पेक्ट्रोफोटोमीटर।
सर यूनिवर्सिटी कब तक खुल जाएगी?